All right, so yesterday we did our lab on Newton's second law. Today I want to kind of get back to being able to look at a Newton's second law problem and determine what type of problem it is, okay, how we get to sum of all forces, how we get to m times a, okay, all of that kind of stuff, just because we're kind of to the point where we need to finish off a bit of the Newton's second law stuff, talk a bit about frictional forces, so we can move on to Newton's third law and then out of Newton's laws and into work and energy. All right, so probably only a couple more days of Newton's second law stuff, and then we'll be moving into Newton's third law and work energy theorem, conservation of energy, okay, which is stuff you took in Science 10 actually. We don't do a whole lot more with it, but that was during online learning, so it might seem newer to you. Yeah. All right, so we're going to have a few kind of vector-related questions to start off here, and then we'll do a few that are kind of inclined planes and a few more vector, kind of go back and forth just to get the hang of more involved types of questions. But before we get to those, I wanted to ask if there was any other questions about the lab from yesterday. I know we got kind of rushed by the time we actually got our data collected, and I don't think anyone really got a chance to kind of sit down and look at the analysis or anything like that, but I'd be happy to answer any questions that anyone had.
We use the decimal like the 0 point, but at least we use the 0.724 for every question.
Yes, because that is the mass of the system. Yeah. Okay. Anything else, guys? All right. I want you guys to give this one a try, keeping in mind that this is a vector-related question. Okay? The key part of this is that the truck, the tow truck, is towing the car, but the car is moving horizontally, even though the force it's using to tow it is angled. The car is moving horizontally. Right? The free body diagram for this can be a little bit involved. Okay, so just keep that in mind when you're drawing it out and then starting to look at your vectored forces for this one. So I'm going to give you a few minutes and I'll draw the free body diagram and vector diagram, and then you guys can keep going. Okay. So we've got a 1,500 kilogram car, so that'll be our mass, and it's being towed by a tow truck. Okay. Now, what they don't outright say is that the car is not moving at 45 degrees above the horizontal, but it expects that we understand how the real world works, and that when you tow a car, it doesn't fly off the ground and move at 45 degrees above the horizontal. Okay? It may be angled 45 degrees above the horizontal, but the car itself is still moving along the ground, right? It's not taking off. All right, so we've got this force here. Okay, and we know that it is 2,000 newtons. And where do I put friction? Going backward. Okay, if the car is moving straight horizontally forwards, friction opposes that directly. Friction always opposes directly. Okay, it's always working against you. It's what slows you down. All right, and that force of friction we know is 500 newtons. All right, so we got to find the acceleration of the car. Now, here's what we have to understand about the vector part of this question. This 2,000 newtons acts this way, but the car is moving this way. How much of that 2,000 newtons is actually pulling forward? Exactly. Okay, this force, this 2,000 newtons, has a horizontal component, that would be the red line, and it has a vertical component. Okay, so this would be like the force vertical, or the force applied vertically, and this would be the force applied horizontally. Okay, I can calculate those because I have the hypotenuse and the angle. And because it's a 45-degree angle, it saves me a ton of work because those two sides are not half, but they're equal. They're the same, right? In a 45-degree angle, it splits it directly in half. All right, so all I have to do then is calculate really all I need is the horizontal one, okay? What I need to understand here is that this force applied vertical, didn't all come.
Okay, this force vertical, try that again. Go away. Okay, so this force vertical goes right here. What is it opposing? Gravity. Yeah. Okay. Now, that doesn't necessarily mean that it's equal to the force of gravity. It just means that it's opposing it. Is there another force acting vertically? Okay, that desk there, it's sitting on the floor. Gravity's pulling, right, normal force. Normal force is also pushing up. If this force here is equal to the force of gravity, the car is literally hanging off of the truck, okay, like not touching the ground. That's not what's happening here, all right? So part of the car is still on the ground. That means part of the car's weight is still pushing against the ground, and the ground is going to push back with however much force is still sitting against the ground, okay? As long as this force, and this force add up to 0, we're good, and they do. And we don't even have to calculate that part. We just have to recognize that it's true. Okay? What we need is the force applied horizontally. So we'll take cos of 45, although it doesn't matter whether we use cos or sine, and go 2 times 2,000, and we find that that force is 1,414 newtons. Right? Okay, so this side here is 1,414 newtons. All right, now that I know that force, okay, and I know that these forces offset, so I can get rid of them. Okay, this force has now been taken care of because I broke it up into its horizontal and vertical parts. The only two forces that are left are the horizontal applied force and friction. Okay, what can I calculate now? F net. So all of this was part of the vector sum of all forces. Okay? So F net is going to be 1,414 minus 500. So we're going to get 914 newtons as our net force. Obviously with the decimals, I cut them off, but we'll keep them in the calculator. All right? If I want to calculate the acceleration, it'll be that 914 newtons divided by 1,500 kilograms, and that's going to give us 0.609 meters per second squared forward, or horizontal, something. Okay, that would give us a vector. Okay, so does everyone kind of follow what we did there? Okay, there's vectors to consider. We didn't need any numbers for any of these vertical ones, but it's still important for us to recognize they're there. They just cancel each other out because the car's not moving vertically. The car is only moving horizontally, which means only the horizontal forces are really playing a part. That's it. Question?
Would there ever be like a question where the force applied horizontally is different than the force vertically?
Yes, absolutely. If I make this angle anything other than 45, that would be the case. Right? If I make it 30, then the force horizontal is much greater than the force vertical.
So then how would you calculate that F net if it was like that?
It's the same way. It actually doesn't, in this case, it doesn't matter which one is bigger, right? I just calculate this horizontal one and go, okay, it is whatever it is. This vertical force, normal force, and gravity, while they might be different numbers, still add up to 0 because the car is not moving vertically. Yeah? Okay. All right. That one's ridiculously easy. We're going to skip that one. Okay, we did one like this the other day. Let's see how many people remember how to do it. Okay. Okay, so just in case you're having trouble getting started, right? What we're looking at here is that situation. Okay, we got a sign hanging from two cables. The cables are essentially identical, angled at identical angles, okay, and they're supporting the sign. Think about what forces are acting here. Okay, I'm gonna add a little more to this. I'm just walking around, I'm seeing most people kind of they're kind of stuck at a certain point, and they're stuck at this point, okay? They know that this is 55 kilograms, and they've calculated that there's a force of gravity acting on the sign that's 539.55 newtons, which is true, absolutely. Gravity is pulling down on the sign. Is the sign moving? Then what's the net force? Right. The net force in this question is 0. What's providing the upward force? The cables. Each one of the cables is pulling upwards. There's 539.55 newtons downwards. There has to be 539.55 newtons worth of force going upwards. It's being provided by the cables. But the cables are pulling at an angle, not straight up. But do they have a straight up component to them? They do. Think about this. Okay, treat them like they're two separate objects. Okay, each one of them has an upward component and a horizontal component, or force Y and force X. Okay? Remembering that the net force in all directions is 0. So that means the two X's are actually canceling each other out. And the two Y's are canceling out this. Okay, I'll give you a couple more minutes because there's one part I haven't mentioned yet. Okay, it's important for getting this, but I think you'll get it. In as much as there are two cables here. Okay, let's have a look at this. There are two cables. My upward force needs to equal 539.55 newtons. How much of that is each cable producing? Half. That's the trick to this question. Okay, is recognizing each one of these cables supports 1/2 of this number. Okay, if I say that each cable holds this number, I have a net force of 539 newtons upwards. And that means the sign is flying. Okay, it's not doing that, it's staying still. So I have to take my 539 and divide it by 2. That is going to be this side, Fy, 269.775. Okay, now that I've got that side, now I can calculate the tension, which is the hypotenuse of this triangle. So I have the adjacent side, the angle, and I'm looking for the hypotenuse. So I'm going to say that the cos of 35 degrees equals 269.775 over the tension in the cable. Right? So to solve for the tension in the cable, I'm going to go 269.775 divided by the cos of 35, which will give me 329 newtons at 35 degrees from vertical or 55 degrees from horizontal. Okay, what do we call that kind of question? Starts with S, not stupid. Static, right? It's a static question. Static means unchanging. All right, the sign is not moving, the velocity is not changing, therefore it is a static condition example. All right, I want to see how much you remember about inclined planes.
What's an inclined plane?
I don't know, but I think you're one wrapped around an axis at this point. You guys know that one, right?
Oh, yeah.
Screw, right. An inclined plane wrapped around an axis is a screw. If you're an inclined plane wrapped around an axis is a screw. It's a Sheldon Cooper joke. I will not claim it as mine.
Well, shucks.
Okay, give this one a try. This is like the easiest type of inclined plane example because it's just sliding. Okay, just sliding down the ramp. Okay, so if we're drawing this one out, okay, we got a 15-degree angle, we've got a 5-kilogram box, okay, that internal triangle is the part you have to remember. Gravity acts straight down and will be the hypotenuse of that triangle. In this case, it'll be 49.05 newtons, okay? Normal force always acts directly perpendicular to the surface. So that means that it's right here. Okay? And when we draw it like that, we end up getting the other part of this triangle to be parallel, if I had drawn it better, parallel to the plane. Okay? So that side's always F parallel. F parallel is always opposite the angle of incline. Force of gravity is the hypotenuse. And normal force, which we still haven't had a need for, but we will eventually, okay, ends up being the adjacent side. Yeah? I always struggled to get that triangle too. It might help to draw normal force first. So draw a line perpendicular to the surface underneath it. Then draw a line off the head of that vertical that's a little longer, and then connect the two. And you always get the triangle right. Over this one. So what we have to understand is what we've drawn here is essentially a vector diagram. Okay? Normal force and gravity act at the same time, and they produce F parallel. Gravity wants to pull the box straight down, but it can't because the plane is in the way. The plane exerts a force perpendicular to itself, and when we add those two forces together with a vector diagram, we get F parallel, which is always going to act down the plane. It is the component of gravity acting parallel to the plane, hence F parallel. Okay, everybody okay with that? Because I often see as a mistake people putting Fg in when they're doing sum of all forces. You've already taken Fg into account when you calculated F parallel. Okay? All the other forces that are going to be involved are going to act parallel to the plane. Friction, an applied force up or down, whatever else there is. Okay? In this case, this is the only force. It's a frictionless plane. Nobody's pulling it up or down. It's just sliding. Okay? So if it's sliding, this is the only force involved. So F net equals F parallel, because it's the vector sum of gravity and normal force. Okay, since I know that, then I can go straight to F net equals m times a. I've just got to calculate F parallel, right? So I'm going to go sine of 15 times 49.05, because I'm looking for the opposite side here, right? Sine of 15. Okay, so that side's 12, so F parallel is 12.7 newtons. Okay, I want to calculate the acceleration, so that's F net divided by m. F parallel is the only force, so 12.7 divided by 5 kilograms is going to give me 2.5 meters per second squared. And it shouldn't be down, it should be down ramp, downhill, down slope, down anything other than straight down. Okay? All right. Ringing a bell?
Yep.
Okay. Try this one. Keeping in mind the words that are in bold-faced italicized print are very important, which is why they're bold-faced and italicized. Okay? They tell you something very important about this situation. Okay, let's just look at the setup for this. Yes. All right, so we have these big ramps, okay, that were used to pull the big bricks, stones that were used to build the pyramids. Okay, so they're angled at 10 degrees. The blocks are huge, 5,000 kilograms, right? And they're pulled at constant velocities. What does that tell us? Acceleration is 0. So thus, what else is 0? F net, right. Okay, so that means that the force up the ramp, which we'll call the slaves, okay, is equal to the force down the ramp, which is F parallel. Right? Not equal to that force, equal to that force plus this force of friction. Okay, so there's two forces down the ramp, F parallel and friction, and there's one force up the ramp, and that's the force of the slaves. All right. So being told constant velocities told me a lot. It told me F net is 0 newtons, and that tells me that these three forces add up to 0. Right? So if I can find out how much force in total is acting down the ramp, I will then know in total how much force is acting up the ramp. Agreed? Okay, I already know one of the forces acting down the ramp is 800 newtons. So that's helpful. Can I calculate F parallel? I can. Okay, so this side here is FG, and it's 49,050 newtons, okay, M times G. And then this side's normal force, which I won't need, and then this side's F parallel. And that angle is 10 degrees. Everybody all right with that? Okay, so F parallel will be the sine of 10 degrees times 49,050 newtons, or times Fg. Right, so sine of 10 times the hypotenuse. Okay, so the force parallel is 8,517 newtons down the ramp. Right? And there's a force of friction of 800 newtons down the ramp. How much force in total down the ramp? 9,317 newtons. Okay, that means there has to be 9,317 newtons worth of force up the ramp. Now, I only have 3 significant digits, so that answer is technically wrong. I should have 9.32 times 10 to the 3 newtons up ramp, or uphill, up slope, or anything other than up, because then aliens would be involved. Okay, it was straight up. Okay, everyone follow what we did there? This is something we always want to be on the lookout for. All right, now, most of the time when I put constant velocity in there, I'm a bit more of a jerk. Because I'll put in constant velocity of 2.5 meters per second. Will you ever use that number? Nope, or at least you better not, because it's completely useless. Okay, you do not want that number at all. But people will substitute it in for acceleration and whatever else, because it's a number, and if Mr. could ever give me a number if I didn't need to use it, yes, he totally would. He's a jerk. Okay, don't fall for that trick. Okay, if it's a constant velocity, it doesn't matter whether that constant velocity is the speed of light. If it's constant, it's not accelerating, and the net force is 0. Okay, just keep that in mind. All right, I can give you another vector one, but that's a little bit trickier. Right, we did that one already. Okay, try this one. It has that same trick. You know, that one I was just telling you about. That's my fish. Okay. All right, so the fish is hooked, and it's being pulled by the fishing line that is angled 45 degrees above the horizontal. Okay? Friction is opposing the motion with a force of 80 newtons, and the fish is moving horizontally. That is the key, or that one of the 2 keys in this question. That the fish is moving horizontally, because that tells me what direction friction acts. Friction always directly opposes the motion. So the fish is going this way. Friction is acting left. Okay, so my force of friction is 80.0 newtons. Alright, and I'm trying to find the tension in the line. Okay, so remember, this force has a horizontal and a vertical component, only one of which is important for solving this question, even though they're equal because it's 45 degrees. So the second key thing for this question, constant speed. Doesn't matter what the constant speed is, it's a constant speed, so F net is what? 0. All right. There are 80 newtons worth of force acting backwards. How many newtons of force are acting directly forwards? 80. Can I now calculate the tension in the line? That's what there is, right? Like, there's not much to this question mathematically. I have to do one trigonometry calculation here, and that's it. But there's a lot of intuitive leaps that have to be made to get there. Okay, so to find the tension, I'm looking for the hypotenuse. Okay, so that's going to mean that the cos of 45 degrees equals 80 over the tension. So tension will equal 80 divided by the cos of 45, which should give me 113 newtons at 45 degrees above horizontal. Okay. That all makes sense now? But it's just those little things, right? We got to make sure when we read a question or, oh, constant speed, write a note, F net is 0. Okay? Like, all those kind of things are all important little details that help you out with a question. Okay, can I put a different one up, or does anyone still need that? No, that one's too easy. All right, since this one will be useful for our, or this one's actually tougher than what we have to do in our lab, okay? Give this one a try since it's the same situation as our lab. Okay, so if we're looking at this one here, it says there's no friction. So what's the only force driving this system? Gravity, right? Okay, so we know that there's a force of gravity pulling on that mass. They tell us that mass is 2 kilograms. Okay, that means that this force is 19.62 newtons. All right, since it's the only force, it is then by default the net force. All right, so I know that my net force is 19.62 newtons. And they tell me the acceleration is 2.15 meters per second squared. What can I find with those two things? Mass. It's the total mass, right? When I do this, it's a system. What I'm calculating is the total mass of the system. So I'm saying F net divided by A equals mass. 19.62 divided by 2.15 gives me 9.13 kilograms. 2 kilograms of which is hanging over the pulley. Right? That's the trick to this question. Is it's just a roundabout way of asking, do you remember that the net force in a system acts on all of the mass? That's all this question is really asking. Okay? Because there's, what, 3 calculations here. M times G, F net over A, and 9.13 minus 2. Okay? Again, nothing here that's mathematically challenging, but there's a few intuitive leaps that have to be made to get there. Right? Questions on that? Okay. I want you to see if you can do that one. It's another inclined plane. Okay, another inclined plane. Okay, question? Yes. What are the key words in this one? Constant velocity. All right, so that means that the forces up the ramp and the forces down the ramp are equal. They add up to 0. Okay, so we know the angle's 9.0 degrees. Okay, we know there's a box sitting on there, but we don't know what the box's mass is. Right? We know there's 800 newtons worth of force acting up the ramp. We know that friction is acting down the ramp with 100 newtons. What other force acts down the ramp? F parallel. How big is it? 700 newtons. That's what I have to get from the constant velocity part. Once I know that, I can use it to help me get the mass. I have to go back to this triangle. Up until this question, we've always been able to calculate Fg using the mass, but we don't have the mass. But that's okay, because this time, we have this side of the triangle. Can I use that side of the triangle to get Fg? Can I use Fg to get mass? Yep. All right, so if I'm going to find Fg, okay, I've got the opposite side, so the sine of 9 equals 700 over the force of gravity. So force of gravity will equal 700 divided by the sine of 9 degrees. Okay, so there's my force of gravity, or my weight. And if I want to get mass, I take force of gravity and divide by 9.81. $456 kilograms. Okay, so again, it's nothing that's, again, mathematically challenging, but there's a lot of little things that demonstrate a good understanding of what's going on in this question in order to get there. All right, try that one. This one you're looking for the incline of the hill. Incidentally, tomorrow's quiz will probably have an inclined plane on it, and probably a vector question on it. Just saying. I'll post an example after school like we usually do. So, every year here in Okotoks we have this soapbox derby race. I must admit I've never seen it. But I see the signs for it every year and say, I should really go watch that.
It's fun.
It sounds like fun. Then I feel like I'm one of those guys that's just waiting to see a crash, and there's something wrong with that. Yeah. All right. So we have to find the angle of the ramp, okay, or the hill in this case. What we know is that the mass of the cart and rider is 65 kilograms. We know that their acceleration is 4.25 meters per second squared down the hill, and we know that friction is opposing with 25.0 newtons. Okay, what can I find right now that will be helpful? Yep, force of gravity is probably something I should find because it's part of this internal triangle. All right, so Fg will be 65 times 9.81. 637.65 kilograms. Okay, that side's normal force, but I won't need it. But I do need this side, F parallel. Okay, and this obviously isn't something I don't know. All right. Okay, so what do I do next? What can I use this and this to get? Net. F net equals m times a. So that's the next thing I should find. Okay, so 65 times 4.25. All right, so my net force is 276.25. All right, what's the other way to calculate net force? Sum of all forces. So F net equals force of friction plus force parallel. And I know force of friction and I know force net, so I can calculate F parallel. Right, so I'm just going to say that F parallel equals 276.25 minus negative 25. Because the force of friction is opposite the net force up the hill. Right? So I'm going to get 301.25 newtons as my F parallel. Well, that's helpful. 301.25. This side 637. I've got two sides of this triangle. Can I find the angle? Okay, so now I can use theta equals the inverse sine of the opposite side, 301.25, divided by the hypotenuse, 637.65. And when I do that, I get that this hill is 28 degrees or something crazy like that. Okay. I don't know where in Okotoks there's a 28.2 degree hill that you could take a soapbox derby racer down. That's more like driving it off the side of the river valley somewhere. Okay? We wouldn't want to do that. All right. Making sense? Okay. Is there a lot of different ways I can ask these questions? There are. Okay, and that's the hard part. There isn't ever anything that's math hard about these. It's figuring out how to get to the math that can be true. Okay? So you got your Newton Lab reports. Those are due on Tuesday. Make sure you're getting those done. If you want me to look them over tomorrow before school or after school, Friday before school, Monday before lunch, after. Okay, we'll be able to look at stuff then. So come and see me. Tomorrow's quiz will be on an inclined plane and a vector question. Tomorrow we're going to go over force of friction and a little bit of stuff about Newton's third law if we get to it. And then on Friday we'll be doing our Newton's second law assignments, and that'll be it for Newton's second law after that. Okay, we'll be moving on to work energy